Okay, so I'm still on page 211. I just finished this example, and there's one thing that I wanted to talk about that I forgot to talk about, I think, last time, and that is the inner loop. So the connection between the inner loop and the rectangular graph is pretty clear once you know what to look for. So if you think about it, when we're tracing this out, so I'm gonna go for it again, right? So I go 0, and then I'm going around, round, round, round. And then right about there, right? So that angle we know is 2 pi over 3. So I start my inner loop at 2 pi over 3. And then I'm going to let me switch colors here. Maybe I'll switch to, what's a good, I don't think this is going to look all that good, but now we're doing the inner loop. My hand's really shaky. And then we stop the inner loop, right? So where are we stopping the inner loop? We're stopping when we get there. So when you're looking at the rectangular graph, you can actually see the inner loop. It's where the rectangular graph is dipping below the horizontal axis. So this part right here, this region is the inner loop. And it's really good to be able to find those sorts of things because one of the weird things you do in calculus a lot is you try to find the area of the inner loop or the area between the two loops or like the total area contained within, where you don't want to double count the inner loop. So we need to know when to start and stop our inner loop. And it turns out that it was those tangent lines that we found. So I just want to go over that, make sure everybody kind of sees that. So here's our inner loop. That's our inner loop, and it came from the part of the graph, the rectangular graph, that was below the axis. So that's just a good thing to know. All right, I'm going to do a couple of examples. I don't know how much I'll explain them as I go, but I mean, you can watch as we do them. All right, so 6 minus 12 cosine of theta. So that's going to take 2 pi. So I'm going to try to like stretch it out a little bit because I know that it's important for me to be able to find and see the zeros of this thing. So 6 minus 12. All right, so, well, let's put 6 here. I'll put 18 here. And then I'll put -6 here. And it's cosine, so it's going to start at a minimum in this case. So we're here, and then here, and then here, here, and here. And we want to fill in the curve. And you want to be like kind of careful about it, because remember those intercepts are useful to us. So you should be looking at your graph and thinking, like, where's the inner loop happening here? And so the inner loop in this particular case is a little strange. So in my opinion, negative cosine limacons with an inner loop, which is like a lot. So negative cosine limacon with an inner loop. I'm really bad at like getting my hand in the camera, it turns out. Are the weirdest of the limacons. So this is going to be our inner loop, which is weird, right? Because you can see that we're going to do like half of the inner loop, then go ahead and do the outer loop. Then we're going to finish the inner loop. The same way that rose curves worked for cosine, right? You would do half of a petal and then do all the other petals, and then you go back and finish that. Same kind of idea here. So I do need to know these intercepts. So let's find those. So I need to find this. I need to find this. And so those happen, we know, when r is equal to 0. Whoa. Okay, so if r equals 0, that means that cosine of theta equals, so we got, I'm going to subtract 6, divide by -12, so that's -6 over -12, so a positive 1/2. And then cosine is positive 1/2 at pi over 3 and also 5 pi over 3. And then if we look at these, it kind of feels right? So it's very close to pi over 2 in this case. And then it's really close to 3 pi over 2. It's like the next closest unit circle angle. there. So 3 pi over, nope, what did I say? 5 pi over 3. 5 pi over 3. Okay, so I'm going to go ahead and dot those in because those are going to be the tangent lines. So pi over 3. So I'm going to start. So remember, you don't like need all of it. You just need the part by the origin. And also remember, if you totally screwed, well, not totally, if you kind of screwed up and you picked the wrong quadrants, you're still going to get the right tangent lines graphically, but you'll be thinking about it a little wrong. So make sure you get those right. And then 5 pi over 3. So I'm going to do this, and then this. So we only need them at the origin. So like even what I drew is like too much. Although the other good points do fall on these lines. So if you're interested in a slightly more accurate graph, you might choose to use those. All right, I'm going to switch to some other color. And we need to be able to go from, we need to go up to 18. So I think I'm going to count by threes. So what I'm thinking is, I'm going to say this is 3. So let's call this 6, 9. So we'll call that 12 and 18. Let me see if I can make this smaller. Just, I feel like it's like really, I mean, that might be better. Let me try one smaller. This is the second smallest possibility. All right, I'm going to go with that. I don't know. Is it good? Let me know. All right, so when, squeeze. Okay, so when theta is equal to 0, whoa. When theta is equal to 0, r is equal to -6. Okay, so you're facing the positive x-axis, but instead of moving forward onto the positive x-axis, you're going to move backwards onto the negative x-axis. So we're going to end up here. So that's where you are when theta equals 0. That's so weird. And then the angle is going to rotate from 0 to pi over 3, right? So I have to rotate 0 to pi over 3. So I'm rotating this. But as I rotate that, now I think it's not thick enough. Ugh, trials and tribulations. Okay, wait, I just changed it so that I think it remains constant now. So it's not pressure sensitive, which is probably like one of the main reasons to get this. But it turns out that I don't like that. So I got rid of that. All right, as we rotate from 0 to pi over 3, r has to go from -6 to 0. So what's going to happen is instead of tracing in this kind of like slice here, we go in the adjacent slice, the like vertical angle, I guess, if you remember from geometry. So I'm going to start here and go into 0 like that. Okay, so that's a first part. And then by the time I get to pi over 2, I need to be up at 6. My scale is way off on that rectangular graph. It now occurs to me. All right, so I'm going to be up at 6. I'm going to fill in my points now. And then by the time I get to pi, I have to be at 18. So 18 should be like here. Okay, so let me go. So I started here. Let me get my face out of the way. I started here and I traced that, and I get to here. And then if I wanted better results, I would care what was happening at 2 pi over 3. But I kind of don't right now. So I'm just going to go for it. So it's going to go out and then there. Okay. So now what I usually do is just use symmetry to like finish this. So I know that if I was up there, like on the positive y-axis, I had to count like 2 tick marks. So on the negative, I'll have to count 2. And that does match, if you look at our graph, when you're at 3 pi over 2, you should be at 6 again. And that's where I put them. Okay, so I'm going to aim for that as I go back in. Just feel more pressure on the way back in because it's like you just have to match the other half. All right, and then from there, you can see it's not going to work because I didn't curl enough. But I have to, as I approach 5 pi over 3, I'm going to go from 6 to 0 like that. And then from 5 pi over 3 to 2 pi, we're negative again. So we're going to finish the inner loop. And there you go. None of these are coming out perfectly, but I think they're all coming out plenty good. So that's what we're dealing with. So the inner loop, so a question that you'd want to answer, be able to answer is, what's a continuous interval on which you get the inner loop, right? So we know that this graph here doesn't actually show us a continuous inner loop. It shows us half of the inner loop here and then half of it here. But we want to be able to say, like, when would you get one full inner loop? So there's two thoughts you could have for that. One is you just keep going forward, right? Like just keep going and that'll finish off your inner loop. I think a slightly better idea, a more common idea, I guess I should say, is instead of going forward, take your graph and go backwards, right? Now cosine's an even function, so if this is pi over 3, then this will be negative pi over 3. So we could say that we get one continuous inner loop. So what happened there? Okay, continuous. Continuous is the worst word. Let's do this. Remember back when I had better handwriting? It might have actually. Let's go back to some former settings. We get a continuous loop. Ooh, that like auto-corrected it. What is even happening? It's kind of like blowing up right now. You can't see it. I can't like undo. Oh, I got it. Okay. I apologize. This app is doing crazy things behind the scenes. Okay, so continuous loop inner, because it really doesn't want me to write inner loop. I'm going to say negative pi over 3 to pi over 3. Okay, and that'll give me one continuous inner loop. And then if you wanted to, you could say that in general, it's negative pi over 3 plus 2 pi n less than or equal to theta less than or equal to pi over 3 plus 2 pi n. N is an element of the integers. That'll give you like every possible inner loop, like every time that happens. That's like a pretty good answer. All right, let's see. What do I have going on here? I think I'm going to do these. If the video is getting long, just stop and come back at some point when you have the time. But let's see what happens. So it's sine, so 2 and 8, and then 2 minus 6 is negative 4. So we're going to go to 2 pi, tick mark, and a tick mark. And all right, it's sine and it's positive. So we're going to go here, 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 up, there, there, and there. Okay, so that's totally wrong. So let me erase all of that. It's it's 6 plus 2, not 2 plus 6. All right, let's do it again. Ready? So we're at 6, and then we can go up to 8, and we can go down to 4. And again, obviously not really scaling this correctly, but we got 2 pi, take mark, take mark. All right, now sine it's positive. There, 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 and there. Okay, here we go, curve. So look at this thing. This thing never intersects the axis, so it's not going to have an inner loop. We never dip below there. It's also not a cardioid, which would just like be tangent to the axis and it would just bounce off. So let's go over here, and I'm just going to plot the important points, right? So it is no, what am I on the wrong? I'm looking at my other computer to see what, so I'm trying to keep track of things. All right, so when theta equals 0, r is going to be 6. We have to go 6 to 8. I think I should count by 2s. So I'm going to go 2, 4, and then 8. Okay, so when theta equals 0, r is equal to 6. I'm going to put a point. So this is a positive sign, so I know that it's like predominantly on the positive y-axis. When theta is equal to pi over 2, I'm going to get 8. So that's here. When theta is equal to pi, I'm going to be back at 6 again, which is 1, 2, 3 out. And then when theta is equal to 3 pi over 2, I'm going to get 4. So that's 2 tick marks out. All right, and now we got to try to fill this in. These are like a little weird. I don't particularly care for them, if I'm being honest. It's like they're trying to be cardioid. So I'm going to swing out like this, swing back in. Okay, so by the time I get to 3 pi over 2, I need r to decrease by 2. So let's see if I can do that. So it's going to go like that. And then it's going to go back out to 6. So there you go. So limacons that don't have an inner loop look really close to circles depending on the ratio or the relationship between the constant and the coefficient. So if the constant is way, way, way bigger than the coefficient, it's going to start to look more and more like a circle. And actually, if it goes the other way, it also starts to look more and more like a circle, but it's just a limacon with an inner loop where the inner loop and the outer loop are like almost the same size. So these are not my favorite, but you know, what can you do? So this would be 6, 0. This would be, I think, 8 comma pi over 2. This would be 6 comma pi. And this would be 4 comma 3 pi over 2. And then the fifth point would close it, and that would be 6 comma 2 pi. All right, so I'm going to stop this video here because I feel like it probably ran a little long. And I'll be back for more.